Okay, let's unpack this. If you follow any competitive team, sports soccer, rugby, basketball, you know that finding the next superstar is often described as, well, an art.
Right, the scout's instinct, a bit of luck, a whole lot of trial and error.
Exactly. But in the age of just overwhelming data, that art is rapidly being digitized.
Hmm.
We're talking about talent identification, or TID, and it is an incredibly complex process. I mean, it involves everything from biology and technical skill to psychology and even sociocultural factors.
And that's our mission today. We're going to try and cut through that complexity by diving deep into how machine learning, or ML, is being used to try and predict the future of young athletes.
And we have a fantastic, really rigorous source to guide us on this.
We do. We're looking at a systematic review titled The Role of Machine Learning in Talent Identification for Team Sports. It's authored by Qingrong Tang, Xiufang and Tan, and it was published in the Journal of Sports Science and Medicine.
So the authors weren't just curious about if ML was being used, but really how, specifically in youth talent ID, so for athletes 21 and under.
Yeah, they looked at everything, the algorithms, the types of data, how the models are validated, and this is a crucial one, how interpretable the results actually are for the coaches on the ground.
The people who have to use it.
Exactly. And, what's immediately clear from their work is the central conclusion. Machine learning, in its current state, shows huge potential, but its role is explicitly to complement, not replace, the traditional approaches.
So it's a tool for the scout, not a replacement for the scout.
Precisely. It's a high-powered decision support tool, a way to generate new hypotheses. That distinction is really key to understanding where we are right now.
That makes a lot of sense because if you look at the history of scouting, it just struggles. TID is so multifactorial, it's long-term, and we've known for ages that just picking one physical measure to predict success, it fails spectacularly.
It really does. And that's the crux of the problem. And it's also why ML aligns so well with the modern way of thinking about talent development. It's something called the ecological dynamics view.
Okay, tell us more about that. What does that view actually mean for how we should look at a young player?
Well, it totally changes the focus. So instead of seeing an athlete as just a collection of fixed traits, they're fast, they're tall, they're strong.
The stats on the back of a trading card.
Right. This perspective treats the athlete as part of a complex adaptive system. Performance isn't based on those isolated traits. It emerges from how the athlete adapts to dynamic situations. We call those performer-environment couplings.
So not just how fast you can sprint in a straight line, but can you use that speed to read a defense and adapt your run?
That's the perfect example. The sprint time is a fixed trait, but reading the high press and changing your passing angle, that's a dynamic coupling. And ML is just ideally suited to model those complex, nonlinear relationships. And critically, it can fuse all these different data streams together, GPS data, psychological surveys, physical tests, to see the whole athlete.
So ML is trying to solve problems that human scouts, no matter how good they are, they often struggle to overcome structurally. And the review points to two really big ones.
Exactly. First, there's the incredibly pervasive relative age effect, or RAE.
Yes, the kid whose birthday is in January.
The very same. It's the systemic overrepresentation of athletes born earlier in their age group. They're just a bit older, maybe a bit stronger or taller than their peers, and that gives them this temporary advantage that completely skews selection.
So we end up picking the biggest kid in the room, not necessarily the most talented one for the long haul.
You've got it. And the second bias is biological maturation. So some kids develop earlier, they hit their growth spurt sooner and get those temporary physical advantages.
And coaches mistake that for long-term talent.
They do. It makes making those long-term judgments incredibly difficult, and it can even lead to burnout for those early stars.
It sounds like a total minefield for human intuition. So how much research is actually trying to navigate this with ML?
Well, the review found 27 studies that met their criteria. It's a growing field, but still, relatively narrow. Unsurprisingly, soccer is the big one, with 13 studies.
Of course.
But it also covers rugby, basketball, cricket, volleyball, and Australian football. The focus right now is definitely on the world's biggest sports.
Okay, let's move to the most obvious use case then. Selection prediction. This is the holy grail, right? Using ML to forecast who gets kept, who moves up, who gets that pro contract. What kind of algorithms are we seeing?
For the most part, it's supervised algorithms. So they're trained on labeled data, players who made it versus players who didn't. And you see the usual suspects, random forest, which is great for this kind of messy, nonlinear data, gradient boosting methods, and various types of neural networks.
And how well do they actually work? I mean, we hear about these incredible ML models in other fields. What did the review find here?
It's a massive range. If you look at a metric like ROC-AUC, which basically measures how well a model can tell a successful athlete from an unsuccessful one, the scores went from about 0.58,
Which is only a little better than a coin flip.
barely, all the way up to an exceptional 0.96.
Wait, 0.96? That sounds almost too good to be true, given how hard this is. What's the catch?
That is exactly the right reaction to have. While some of these models look amazing on paper, the key finding is that the accuracy was usually high internally, but it was rarely externally confirmed. That 0.96 is often a sign of overfitting or some pretty weak validation methods. We definitely need to get into that later.
Okay, but first, let's talk about the data itself. The review gives us a really clear contrast, right? A spectacular failure and a holistic success.
It does. Let's start with the failure. It's a striking example from an elite Scottish soccer academy with a 10-year follow-up.
10 years? That's a lot of data.
A huge amount. And they tried to build models to predict who would get a professional contract using only anthropometric and physical test data. So things like height, sprint times, how high you can jump.
The traditional combine stuff?
Exactly. And the result? The prediction accuracy was near random guessing.
You're kidding. After 10 years of tracking these elite kids.
I'm not. The error proportion was between 0.43 and 0.45, where 0.50 is pure chance. It means the model gave them almost zero predictive value. They basically wasted a decade chasing features that don't separate the good from the great at that final step.
That is incredible. It confirms that once you're in an elite group, everyone is fast and everyone is strong. Those things get you in the door, but they don't predict who signs the contract.
Precisely. But when you look at studies that took a more holistic, multi-domain approach, the picture changes completely.
So what kind of non-physical data really moved the needle?
The review highlights studies on youth rugby union selection. The successful models didn't just look at grip strength and sprint speed, they integrated sophisticated psychosocial measures.
Okay, so what does that mean, like personality tests?
Things like that, yeah. They found that psychological factors, specifically things like lower burnout, reduced exhaustion, and better coping with pressure, were actually critical predictors of who made it through the system.
That's a profound finding. So ML didn't just confirm that physical skills matter. It proved that once you're in that elite group, it's the mental and emotional factors that give you the real predictive lift.
It really shifts the focus. It's not just how fast are you, it's how resilient are you. Performance is emergent. It's how a player uses their physical toolkit while managing the enormous psychological pressure of that elite pathway.
So let's look beyond just the simple select-deselect models. What about tools that a coach could actually use day to day, like for team formation?
Yeah, this is a really practical area. Models like random forests are getting very good at this. One study in youth soccer showed they could predict player positions and generate lineups that were almost identical to what the coaches chose, with about 94% accuracy.
That's impressive.
It worked especially well when they combined the coach's own subjective ratings with objective data from training devices, like GPS trackers and passing metrics.
So it's a powerful way to either confirm a coach's gut feeling or maybe even offer a surprising suggestion based on the data.
Exactly. And another big area is helping get rid of one of those biases we talked about earlier, maturation prediction. This is where explainable ML is proving to be a game changer.
How does that work?
Well, a model can accurately predict a player's biological maturation status, like their age at peak height velocity, using simple, non-invasive things like sitting height, weight, and grip strength.
So the coach gets a number that says, hey, this player's dominance right now is probably because they're an early maturer.
That's it. So the coach can manage expectations and training loads differently, and they can avoid misclassifying that player as the next big thing just because of their temporary size advantage. It's a huge tool for reducing that bias.
Absolutely. Now, I want to get to what the review called out as a real aha moment. It had to do with specialization risks in youth basketball.
This was a fascinating study. They used unsupervised ML clustering to analyze shooting patterns in U14 players and then compared them to professionals.
And what did they find?
The results were stark. The U14 players showed clear signs of premature specialization. They were really good from 2 to 4 specific spots in the mid-range, but they lacked versatility.
So if you forced them out of their comfort zones, they were kind of lost.
Completely. And in sharp contrast, the pros were either these highly versatile players who could score from anywhere, or they were hyper-specialists in a single, really high-value zone, like the three-point line.
The U14s were specialists, but in the wrong way. They specialized for their U14 league, not for the skills needed to become a pro.
That's the crucial implication. It suggests that our youth competitions might be rewarding short-term success winning this weekend's game over the long-term development of versatile skills. ML exposed this huge disconnect between how we train kids and what they actually need to succeed at the highest level.
That finding alone should make every youth sports director pause and think.
Okay, so we've talked about all this incredible potential. We've seen these .96 accuracy numbers, but now we have to face the cold, hard reality. Why is the overall conclusion still so cautious? In a word, rigor. Or, the lack of it. The review used a tool called Probast to assess the risk of bias in these studies.
And the finding was not good.
It was pretty damning. 16 of the 27 studies, that's almost 60%, were assessed as having a high risk of bias, mostly in how they analyze their data.
So that really puts a question mark next to those high accuracy numbers we were talking about. What were the core issues here?
The biggest one, by far, is validation deficiency. Very few studies used rigorous methods, and almost none of them used the most important one, external validation.
So that means testing the model on a completely new set of data, right? Like from a different team or a different season?
Exactly.
Yeah.
And when you don't do that, you create this huge gap between what we call apparent validity and transportable validity. Apparent validity is that inflated .96 score you get from testing the model on the same data it was built on. It knows all the answers to the test.
And transportable validity.
That's the real question. How well does your model generalize to a new group of players? What worked for a Dutch academy that focuses on skill might fail completely in a Brazilian program that prioritizes physicality. If you don't validate externally, your model can't be trusted to cross borders or even seasons.
So a coach in England can't just pick up a model from Germany and expect it to work.
They absolutely shouldn't. And on top of that, the review found that crucial metrics like calibration performance were almost never reported.
Okay, what is calibration and why does that matter so much to a coach?
Calibration basically ensures that a model's confidence is trustworthy. So if a model tells you player A has a 90% chance of being selected, a well-calibrated model means that if you took all the players it gave a 90% chance to, 9 out of 10 of them should actually make it.
So if it's not calibrated, the model's 90% confidence score is basically a lie.
It's meaningless. And without that information, a coach has no idea how much to trust what the model is telling them.
And I'm guessing the old problem of small sample sizes popped up too.
Oh, for sure. Some studies had as few as 21 players. A model can just memorize a data set that small. It gets 97% accuracy internally. But the second you show it a new player, it completely falls apart. It's just overfitting.
So the research community has some serious work to do before these tools can be trusted in the real world.
A lot of work. They need to prioritize transparent reporting, they need to report calibration, and most of all, they need to do external validation. Future work really has to adopt standardized guidelines, like something called Tripiod plus AI.
And what's that?
It's basically a checklist that forces researchers to be totally transparent about how they built and tested their model. It makes the research auditable, which is fundamental for building trust. And we also need to audit these models for fairness. Do they work equally well for early and late maturers, for example?
Which brings us right back to that central conclusion. These tools are exciting, they're revealing new things, but they are absolutely not ready to be the sole selector.
That's the bottom line. ML's current role is exploratory and complementary. Its value is in augmenting human expertise, highlighting patterns a human might miss, and helping with monitoring. But if you over-rely on these unvalidated models, you risk just reinforcing the biases we already have, or worse, making really misleading decisions.
So looking forward, if we fix these rigor problems, where does ML go next in sports?
I think the next evolution won't just be about predicting who is talented now. It's going to move into personalized intervention. We call it counterfactual reasoning.
Counterfactual reasoning. So asking, what if?
Exactly. Using validated models to simulate how specific changes in training might actually alter a player's selection odds. A coach could ask the model, what if we increase this player's training volume by 15% and focused on their coping skills? How would their odds change in 2 years?
Wow.
That moves ML from just describing an outcome to helping you actively engineer a better developmental pathway for each individual athlete. That would be truly revolutionary.
That capability, personalized, prescriptive intervention, that is where the real value is. This has been a fascinating look at a field that's both exciting and clearly in need of some serious scientific discipline.
It really provides the nuanced understanding you need to navigate all the hype.
To our listeners, if you want to dive deeper into the case studies and the critical methodological points we talked about today, we really encourage you to read the full article. That's The Role of Machine Learning in Talent Identification for Team Sports by Tang, Wei, and Tan. And be sure to follow us and turn on your notifications so you can keep learning quickly and thoroughly with all of our deep dives. We'll catch you next